又才
Yeah, but lecture one, I think I did not complete it. I just want to tell you that this part is dealing with the operating system. I will not cover it. Okay? It's just that you're using different operating system for distributed system rather than single computer system. Okay? So that is sorry. Okay, distributed operating system is another operating system that you use in order to do distributed system. This lecture one, I missed this. Okay, actually, it just tell you that it's a different operating system that is used for distributed system. Of course, you can use Windows operating system or Linux, which is not meant for distributed operating system. But this distributed operating system that is discussed here is the specialized operating system meant for distributed system. Okay, I'm not going to discuss much about it. Just make you aware that there are distributed operating system in place in order to make the programming for the distributed system much more easy. Okay, so this is lecture one, which I missed. Now the second part, I think I stopped here last week, right? I was talking about DCP, and I mentioned to you that on top of DCP is the IP layer. Sorry, it's on top of the IP layer, which is the transport layer, layer 4. Okay, your application is on top of this application, on top of this transport layer. So you got physical layer. On top of it is a link layer or media layer. Then you've got an IP layer, which is the network layer. Okay, on top of that is a transport layer. So the transport layer, you have TCP, the one that is well known, UDP. So there are two that is specified in IP stack. And IP actually has only maybe 5 layers only. Okay, of course OSI layer got 7 layers, but here is already the application. So the application is on top. So HTTP is the web, is the application layer. Okay? FTP is a file transfer protocol, also is the application layer using this. Okay? Telnet, also the same thing, is the application layer using TCP as well. Of course, there is some other application layer that is using UDP. Okay? And we have a new transport protocol, which is a connection-oriented new one to replace TCP. It's actually at the top here. I don't know what you call that. Okay, it actually uses UDP. Okay, it uses UDP to transmit. UDP is connectionless, but itself is connection-oriented, and that is maybe we're going to use it in the future to replace TCP because TCP is a bit slow. Okay, the same thing for the simple mail transfer protocol, which is for mail. Use this protocol. There's also application program running on top of transport layer, and it is using TCP. Okay, so that is all the network. Now there's another way to actually share the data. Use pipe. Now this pipe is you can view it as shared memory. It doesn't use network. It uses memory to share the data. So you have let's say this is your program. Okay, and you need to communicate with another program. It's called process. Process A. Okay. And what you do is you create a file. And this file is, although it's called file, one thing funny about Linux, I'm talking about Linux now, because type actually comes from Linux operating system. I mean, not Linux, Unix system. All the Unix flavor like Linux, BSD, they're all Unix system. So in Unix system, file, we always view it as a file that is stored inside the storage, right? For example, in hard disk, it's stored in hard disk. So basically, it is file that is open, closed, and when you read or write into the hard disk. Okay? But actually, file in Unix system is not necessarily in the hard disk. It can be stored inside the memory. So you open the file, and that file can reside inside the memory. So this part here is a file, and this file actually open inside the memory. Okay? And process A can open it, and then you put the data inside there, and then you share with this process B. And this process B will consume it. Now, it does not go through the network. You only use the memory. Of course, you can also flush it into the storage. It can go into the file system as well. Sorry, the storage system as well. But then that will be slow. But most of the time, when it creates file, normally it creates it as a file which resides inside the temporarily resides inside the memory. Of course, so when all this process is deleted, of course the operating system will store it inside the file storage. If let's say it finds out it has to be retained. Okay? Now there are two types of pipe. Let's discuss them. First one is ordinary pipe, and the second one is named pipe. So what is the difference? Ordinary pipe is it doesn't have name. Okay, named pipe, as the name suggests, it has names. Okay, meaning that when you create ordinary pipe, you create a file, but that file has no name. Okay, it resides in the memory, and then you can pass to the process B. Maybe it doesn't pass to the process B. Maybe it passes to its own threads. So this thread communicates with this thread. Of course, you can pass to another process as well, but you can use it within the threads, within the process. So you have multiple threads inside the process. Okay, so you can share the data through this pipe, ordinary pipe. So this pipe has no name when you create it. The other one, you create a name. So this one looks more like a file. So when you open it or you create it, it's just like you're opening a file. A file inside a secondary storage, let's say your hard disk. All right? And it has a name. Now, if it is open and is in use, normally it's inside the memory, which is named pipe. But if let's say it's closed, that means this process A and process B gets closed or terminated, this eventually will be pushed to the file system. Okay? Because name pipes, when you create it, if you don't close it or you don't delete it, it will remain inside the file system. First, you go into the memory first. If it is not used, and the computer wants to use the memory, it saves it into the file. Okay? So that next time when this process A and B comes out again, it can use this pipe again. So this pipe can live longer than the process A and process B. What I mean is it lives longer than the process that created it. Okay? Whereas ordinary pipe, it has no name. Once the process is deleted, the ordinary pipe is also deleted. Okay? It has no name, it does not cease. Okay, so that is the difference. Okay, what is the similarity? There are pipes. Pipe means it's just like a pipe that you see there. Just like this pipe. You pass it in one interface, in one entry, and it comes out in another interface. Okay? It's unidirectional, that means you can go in one direction. So if you want to communicate in two ways, you have to create two pipes, like this. Okay? Two pipes. The first pipe will go this direction, the second pipe will go this direction. That means if you use name pipe, that means you've got two different pipes. For ordinary pipes. Okay? Now, how about name pipe? Name pipe also the same thing. You take two pipes and then you send in two directions if you want two of them. Okay? Alright, so what is this, how does the pipe works? If you put the message in, let's say you put the first message, right? But let's say this the receiver here is lower, then you will place it inside the buffer. So the pipe actually has a buffer. Put the message. If it is not consumed, you'll be there waiting for the receiver ready to receive it. Let's say the sender is faster. You keep on accumulating inside this pipe. Okay? Actually, I draw it wrong. I shouldn't draw it this way. I should draw it this way. Okay, you accumulate like this. So this is the first one. The second one will be here. The third one will be here. Okay? Because when the receiver receives it, you pop up the oldest one first, not the latest one. Okay, so when you push in, you go in like this, and then when it comes out, you come out the first one. So it's first in, first out. Okay, 5-4. First in, first out. First to go in, first to come out. Okay, last to go in, last to come out. Okay, so 5-4 will ensure that it's in order because you want the first message to go through first. You don't want the last message to go through first, right? So you must first in, first out. Okay? So the buffer is first in, first out. And that actually is something to do with a mechanism which we call producer consumer. We discussed this in chapter 3 and chapter 4. We use this producer and consumer as an example to demonstrate race condition and some other problems. It's actually a useful mechanism, and you can see that actually used. If you want to know how it is used, actually in my practical, I have some. Maybe I'll show you how it looks like. It is inside this collar. You choose any one, maybe the first one. Actually, inside all of them have it except the last exercise. Inside this corner here, here I use pipe. See that? This pipe is in C++. So when I open the pipe using the normal file open function. So you treat this pipe just like a file. And this is a name pipe. I have a name. What is the name? The name is given by the caller. The caller passes the name, and then I create the pipe. Okay, and this is right only. And then, okay, this is my C++, opening the pipe. This is one process A. Okay. And then there's another process, Python. This is running C++. This one is running Python. Okay. So my Python, I also open the file. Sorry, this is the one that create the file. Just now it's open for reading. This one is the one that create the file. Okay, open the file. So this is Python. Open the file, and then you start to communicate by passing the data. So it's pipe read, pipe send. Here is pipe read. In the C++, I pipe send. So pipe send, pipe read. Okay, so these two processes, two different programs. This is C Python, this is C++, so I communicate with one another. Okay, here I use it because I have to overcome one problem. Maybe when you do this exercise, you will understand why I did this. I actually explain it inside. You can have a look at it. Okay, so there is one demonstration of using name pipe. Just now I used name pipe. I have a name, so I pass the name to the other process. So this guy created, and he passed the name to process. So process A use that name, open it, and then send the data in. On the other side there, Python receive the data. Sorry, let's come back to here. Okay, this one you don't have to close it. Once the creator gets closed, the operating system knows the ordinary pipe is opened by this process, and you automatically kill it. Okay? And where this pipe is stored, actually, is stored inside the process control block. So that's why you have to put process control block. Process control block does not only store your register, it also store this file that is opened by the process as well. So whatever file that's opened by this process will be recorded inside the PCB, which is a process control block. So when the operating system kill or terminate this program, you look at the process control block, you see what are the pipes that is open, when you detect that, you will automatically delete it. So you don't have to explicitly close it. Whereas the name type, you have to explicitly close it. Why? Because when you create a name, it's just like a file. Initially, it's staying in the memory to be fast, but if let's say this process is gone, it will save it into the file, and it persists. It persists there until you delete it. Why? Because you might want to use it in the future. Maybe this process is closed because you want to shut down. Then when you open up again, if this part is still there, this name part is still there, you can still open and use it. Okay? So that is the purpose of that. That means it can live beyond the lifespan of the process that you created. So you have to explicitly delete it. Okay, so message passing is one way to actually do communication. Of course, it depends on you. It depends on how you actually implement the protocol. You have to create your own protocol in order to manage it, right? So it's not so easy. If you want to do distributed system, everything is in raw mode. That means you have to program yourself. That's why we come out with they come out with this message passing interface, which we will learn later on. We learn OMP. Next, we're going to learn MPI. Okay, so what is the difference between OMP and MPI? OMP at the moment is shared memory parallel computing. Message passing interface actually is both. It supports both. It supports shared memory. It also support message passing. Okay? It supports both of them, and it will decide if it knows that the process actually lives in the same system, in the same computer, then it will use the shared memory. Otherwise, it will use message passing. So it is done behind the scenes. You will not know. Okay. Now, OMP. One bad thing about OMP is this process needs to be run on the same computer. Okay, computer system, what I mean. Okay, so a computer system does not mean you have only one processor, because one computer system can have multiple processors, right? Multi-processor computer. So this process can run on different processors, but they all share the same memory. Okay, they have one big memory that is shared. So because they have a shared memory, that's why they can use OMP to run this program. But OMP does not support distributed system or distributed parallel computing system. If you want to do that, then you have to use MPI. Okay? So MPI, it has you can run on the same machine. You can also configure two different machines. Maybe, okay, your exercise don't have how it is run in two machines. But if you're interested, you can go and find out how to do that. Because internet, you can find a lot of information. Maybe I can show you also, but there's none inside the practical. You create two, and then you tell MPI the cluster of computer that needs to work together. You put in the IP address inside a file, and then when you run the MPI run KCC to compile, and then it will run these two programs. And how does it communicate? It will do it for you. Okay, so it's not raw. Like message passing, you have to do it yourself. You want to do distributed system, you want to run them in parallel, you have to monitor, you have to coordinate, you have to do everything on your own. But when it comes to message passing interface, which is a platform, you don't have to do it. Although it is using a network whenever necessary to do the job. Okay? So this is a very popular parallel processing platform, which we will learn later on. Right? It uses a network when the two system is actually converted by network. Okay, so how does the message passing model in abstraction, how does it work? I've shown this picture before. This one is a bit more detailed. When this process run on a computer, then maybe this run on a separate computer. You have a variable that you want to send across. You have to create a copy first. Okay, you create this copy and then you send over the network medium. And then the other side, when you receive, you create a memory to store it. So you've got two storage allocated to store this data, and also a copy that is transmitted through the medium. So this is actually slow, and also it's not so efficient. Of course, if you want to use a distributed system to do parallel computing, you have no choice but to do this. Okay. Now the details of it is, if you want to send this variable across, you have to use this function called send. Okay, you pass in the variable, and then you have to specify the size. 2 here means 2 bytes. Okay, and then message ID basically is the ID of the message, so that the other side when you receive knows what it's supposed to do. Okay, so on the receiver side, you call this function. Same thing, you receive, and then you store it inside the variable. Of course, you have to allocate it first. Then the message ID that you receive, and then you interpret the message ID to find out what is the command. Okay, so that it knows what to do with the data that you receive. Okay, where is it used? Message passing is widely used in the past and also now as well. In IBM Blue Gene supercomputer, because in the past it's supercomputer, but right now it's no more supercomputer because our computer also has the same speed as this as well. Okay, this one is an old supercomputer. And how do they create this supercomputer? They don't have one processor which is very, very powerful. What they do is they create a distributed system. Okay, so each of these rack here contain processor. You can see this is a processor on the motherboard. And then on one rack, you got multiple motherboards, this processor. So this is one rack, or they call it card. So here is card, this is rack. And this rack is placed inside the cabinet. This is the whole system that you see here. So they need to be wired up together to communicate with one another. You can see here, there is a router at the top. The bottom here is the PSU, which is the power system, power supply unit. And then at the front, this is at the back, at the front, inside is this card. Okay? And they communicate using this network. Most of it is it. Okay, and that is a cheap way to actually create a supercomputer. So most of our supercomputers nowadays are distributed systems, and they are not single computer. Not like in the past, to create a computer is a single powerful computer, supercomputer. After that, they find out that it's not so cheap to do, and you cannot scale. That's why they move on to distributed system. Okay, so that's why distributed system is important when we discuss about cloud computing. Okay, when you have distributed systems, so how do you get the processors to do the work? For example, here, as I mentioned to you, you got a lot of tasks to do, and this task may be run in parallel. How does the process A ask process B to do a certain job? Okay, one thing is to do message passing. So you can see, you can view like this. Message passing. Okay, is down at the bottom here. Let's say this one is MPI. Okay, so this you have to still, although you handle most of the thing, but you still have to make sure that if you use TCP, of course, that is the worst one, because you don't have to help all, you have to write your own protocol. So this is difficult, very difficult, because you have to do everything yourself. Okay? And message passing, we are going to use this platform later. This one, difficult still, but easier than this. I will write in moderate. Okay, the difficulty is moderate. Okay? Then on top here, we use another technique, which is much easier than MPI. Is RPC and MPI. RPC, also RM. Okay? So this one is easy. Okay? So you can use this, or you can do your own, right? And what is the difference between these two? Actually, they are kind of different. This one is meant for distributed system and run in parallel. You see this P here, this P is message passing, but the whole thing is actually to do parallel computing. But this one does not mean that you need to do cloud computing. But this is much easier to program compared to this. This actually invoke function if it is RPC, or invoke method in a class if it is RMI. Okay, so both of them is the same. This is for object-oriented programming, like Java, C#, or C++. This one is for C language, or any languages that is not object-oriented. But most modern languages are object-oriented. Okay, so non-object-oriented is like C, Pascal, maybe you learned before, Pascal, COBOL, or Fortran. They are still in use. COBOL especially used in business, like banks. Fortran is used in scientific community. C, we are still using it. C++ is here. Okay? So the two is actually difference is one is object-oriented, the other one is not. Okay? And what is the difference between these two? This one you pass only the message. This one is called message passing. This one you pass two things. You pass the message. You also invoke a function. So this is just like you're calling a function. Let's say main calling another function here, right? But if you want to call a function that is remotely, let's say this is the network. Okay? So this function here is actually on a remote computer. Your computer is here, but you want to invoke this function here. Of course, invoking your own function is very easy, right? So you want to invoke another function that is remotely located, then you have to use either RPC or RMI. Okay? So it appears to you, when you call it, it appears to you just like you're calling a function that is residing in the same computer. Actually, that function is residing in another computer. Okay, so that is remote procedural call or remote method invocation. Okay? Both of them are the same. One is non-object-oriented, the other one is object-oriented. Okay, so this is how it is done, and it has a stub. Okay, the stub of .c to help you do that. So this stub will appear with this local program as the actual program. Actually, it's not a program, or the actual function that you're calling. So you're calling this stub, you're not calling the remote. When you call this stub will transport the data across. Okay? You transport it to the next stub of .c, and then this will interpret it, and then you call the remote procedure. Once it's done, you return the result, and the result is passed to the stub again, and the stub will communicate across the network to this other stub, and then this result is returned back to the caller. So from the caller perspective, it is calling the local function, which is true. It's actually calling this stub. This stub does not know anything. It does not know how to do it. So whatever command that is received from this caller, you just pass along the network to another stub. And this stub also do not know anything about it. It does not know how to solve the problem. And what it does is you call the remote procedure, and the remote procedure is the one that we need. Okay? Okay, how does the data get transported? Let's see for data. You'll be handled by the stub as well. So you use message passing, the same protocol. So this actually runs on top of this message passing protocol. Okay? Sorry, I shouldn't write MPI there, because MPI is one of the platforms. Okay? MPI is one of the platforms that use message passing, just like RPI. So RPI actually uses message passing to transport the data across and also call function or invoke the function. And this is how the middleware is doing the job. So the middleware is at the top. Okay, so when you program middleware, you're actually using either RPC or RMI to do distributed system computing. Okay, because middleware is actually a software that is a distributed system. Okay? So this is how middleware look like, the process that's running. This process you don't need to know where it is run. So to all this process, they look at this system as one system. They do not know that they are actually separate computer systems. This computer does not need to be homogeneous system. That means same computer. Let's say Intel. It can be Intel. It can be different processor, maybe ARM processor or whatever processor. Okay, so the middleware is going to handle it. But for the process, this system is one homogeneous big system. Okay, so that is the end for this chapter 2. Okay, now we move on to chapter 3. Chapter 3, we want to talk about memory management system, how you manage the memory. Because when you do distributed system, memory is part of the things that you have to manage. And you can see, I think some of you, maybe only the first group saw this part here. Whenever we deal with any parallel computing or distributed system, maybe you haven't done this part yet. The parallel computing, you have to allocate memory, right? Allocate memory and then you have to deallocate memory. So somehow you need to manage memory. Okay, in distributed system, of course, you can have centralized system, but most of the time it's distributed memory. Okay, but if let's say you are talking about parallel computing, most of the time the memory is centralized. Okay, so the first part we're going to look at centralized memory management. How does it do? How much does it manage it? This is just a review. I believe this you have learned this in your operating system course before, right? Before you come to it. We're going to touch a little bit on it. Okay, what we have inside this memory management, we're going to look at two different servers, right? The simple memory model, and then the shared memory model, the distributed shared memory. And if we do distributed shared memory, how do we do a memory migration? We'll talk a little bit about it here, and then we'll talk some more in practical form. Okay, so as your computing tasks get larger and larger, of course you need to also scale your computer system. Otherwise, your performance will not improve. You will see performance degradation, right? So your task getting larger and larger. You also need to scale your computer system, whether it's vertically or horizontally. Okay, in this case here, maybe it's horizontally. Okay, horizontally means a new computer system to scale it bigger and bigger to accommodate this larger task. So when you scale the system, of course you have more memory, you have more secondary storage, and the processor will also, there are more processors, so you can crunch more data in parallel. If let's say it's scaled vertically, then you may have a faster CPU, okay? Because the scale vertically means you improve the processor. But if you scale horizontally, you're just adding processor. And of course, with this larger or many more processors, you can do multiple computations simultaneously, and therefore that is how you get your performance gain. Okay, this is just a review. I believe you all learned virtual memory before, right? In the operating system. Okay? So you must have heard about paging. Have you heard about paging before? And segmentation. And how about page displacement algorithm? Before we go into that, do you know what paging is all about first? Yeah, here there's not much slide there. Actually, it's just a review. I'm not sure why they put it up there, but no explanation at all. But let me scratch it here. A quick one. I don't have enough time to discuss. Of course, it's related to what we do, so maybe you need to know a little bit about it. So let's say you have a computer, and you only have, let's say, 1 gigabyte of memory, right? 1 gigabyte of physical memory. Okay? And one of the use, I'm just showing you one of the use. Of course, virtual memory actually is more than that. But one of the use which I think most of us can appreciate is how do we make the computer, the CPU, to see this physical memory which is not this size but is much larger. Maybe 64 gigabyte. Okay, so this is virtual memory. So it's just an illusion to the CPU. The CPU will see this virtual memory. It doesn't see the physical memory, it sees this virtual memory. It sees it's larger. Okay? So the whole idea is actually to make it, actually it's not just larger, it's actually more than that, but just to simplify it, look at it as a larger memory, but you don't have that memory. That's why it's called virtual memory. Okay? So where does the memory come from? It's actually a combination of physical memory plus the storage, secondary storage. Okay? So that the CPU sees this memory exists and is big. Because this one is small, this one in the secondary storage most probably got terabytes of size storage, right? So, but then how does the virtual memory trick the CPU to see this appear to the CPU as a large? So actually, the CPU, whenever it touches, it can actually access all the memory. Although the physical memory is only 1 gigabyte, but it can write into all of that. But how does the virtual memory management system, or MMU, does that? This memory management unit actually is part of the processor. It's down below. So this is the processor. Inside the processor, you've got many components. One of them is MMU, memory management unit. So the memory management unit is the one that creates this virtual memory for the CPU to see. Okay, so how it does it? It actually does it using paging. That's why paging comes into play. Okay, so how does it do it? Page means you have some size, let's say 64 kilobytes, so you have many of them, right? So first, when the computers want to use, let's say for example, this is 1 gigabyte of memory, so you use this memory, let's say here, okay, you use it, fine, and this one is actually mapped into here, right? So whenever it touches this one will go into here, when it touches this, it will go into here, okay? But then when you touch the second part, but this second part here, it's not there, this memory is not there. This size is all covered here. Now how does the CPU able to touch this unavailable memory? What it does is this, you check first. Which of the memory that is not used, frequently used? The one that not frequently used, save it into the secondary storage. And then you make this appear here. So you map this page to this. And of course you load whatever data was there for. So when you touch it, actually you go to this physical memory, the same physical memory. But what happened to the old data? The data is saved here, blurry. So that when you come back here to touch it, you will load it back. So to the CPU, this memory appears as 64 gigabyte, and it's there. But actually it's not real. You use the physical memory and the secondary storage in order to trick the CPU to think that that memory is there. Okay? And paging is to trick or to solve that problem. You have to page in, page out. Page in, that means you page in from the secondary storage into the actual memory. If there's not enough, you page out the least frequently used one, page out, and then you page in the one that is you are touching, so that when you touch it, you will map into here. So how does it map here? We use an algorithm to convert the address into here. Just like what you learned in your 8086 You've done segmentation, right? But you haven't reached this part here. This part is actually more complex. The A0, A6 is a simpler one. This one's more complex. So you have some algorithm to convert this address, linear address or virtual memory address, into the physical address first. So for the CPU, you look at the virtual address, but the actual address is the physical address. So there's a translation that happening behind the scene that translates into this address. Okay? So that is a paging. Now there's another part which is segmentation. Segmentation is nothing to do with virtual memory. Actually, segmentation appears first, but Intel found out that maybe the computer scientists discovered that segmentation cannot solve a lot of problems. So that's why they come up with virtual memory and paging to solve the problem. Okay, I will not go into the detail of segmentation and the difference between these two. Actually, they are different. Although a lot of people say that they're the same, actually they're solving different problems. Of course, page replacement algorithm is the one that I've mentioned. How to see page in and page out, which one that you choose to page in and page out, right? Of course, you don't want to page in and page out so many times, because let's say you touch here, and then you touch this, and you touch it, and you page in and page out. This transferring of data into the second storage and in and out is not going to be slow, right? So if you do that, that's why your computer, you can hear that. Sometimes your computer slow down, and you hear the hard disk working very hard, right? Actually, is having this page caching problem. Page in and page out because you don't have enough memory. Okay? And the CPU think that you have enough memory, so you go and touch here, touch there, and then you trash this physical memory in the secondary storage. Because you have page in, page out, page in, page out. So you hear the hard disk keep on transferring data. Okay? And then you see your computer slow down and you run out of memory. Actually, you don't run out of memory. You excessively use the memory. Okay? So you open the browser and you open a lot of trackpad. Then you see this problem happening. Okay, so I basically explained about the simple memory model. Just now it's actually virtual memory. A simple memory model is just like an 8086 where it does not have virtual memory at all. Your CPU actually look at the physical memory, and that is what we have, and that's it. Okay, so 8086 does not have virtual memory, so you only see this, and that is a simple memory. Okay. Of course, the more complex one, intermediate or advanced memory model is the virtual memory. Okay, the second one is the shared memory model. The shared memory, actually you can use virtual memory to help share the data. Okay? Let's say, for example, you can do something like this. You can say, the process A, look at this data here. Okay? And then process B will look at this data here. Okay? And then both of them actually map to the same page. You can do something like this. Although different address, but they're mapped into the same physical memory. So this process A, whenever I write into here, the process B is able to see because the window is looking into the same physical memory. You can actually do that. So virtual memory management, memory management unit can actually help to do this kind of sharing. Okay? Because there are many ways to do it, but this is one of the ways that you can employ in order to share your data. And of course, you can share the data directly. Use this address by process A, and process B can also use it. Actually, cannot. No, you can't. Because process A and process B have their own virtual memory, different virtual memory. Okay? So their address is also different, but into the data is the same. But what I mean is one process will have multiple threads inside there, right? So these multiple threads can share the same memory, yes, because they can touch their own memory. But process B, they have their own virtual memory. They're sharing the same physical memory. But if you want to share, then this memory here, virtual memory of process A, will let's say reside on this address, let's say 0x100. But process B, it has the same memory shared which is the same physical memory, maybe it's a different address. Okay, so when you write into here, it goes to the physical memory and it's able to see by process being produced. So this is how processors share the memory using memory. Okay? Because this virtual memory, there are different virtual memory. Okay? Why do they do that? Why the operating system separate the virtual memory for two different processors is because you don't want this process to corrupt the memory of this process. Okay? If let's say they share the same virtual memory, process B can go and corrupt some of the data here. But you have a separate virtual memory, then there's no way for you to corrupt. You can only corrupt those that we share. Right? Okay? And this also will prevent virus from attacking your processors as well. Because if let's say the process is created and that process is infected with virus, you cannot go and write anything on other process. You can write only in the process that is infected. That's how the operating system contains the virus. Okay? This is not available in earlier processor because earlier processor we don't have virtual memory. That's why in the past virus is very hard for you to stop. Okay? But once we move to a new processor, we have virtual memory and therefore things are much easier for the operating system to prevent virus from spreading. Okay, this one I think I explained to you in the class already, so I'll just skip it. Basically, you have multiple level or layer. We call it level, right? Level 3, level 2, level 1 cache. Why do you need cache? Because you want to expedite the processing, right? Because the external memory is very, very slow. This physical memory which is outside the processor is slow. It's slow because of two things. The technology used to implement them is slow. Second thing is the speed of light. Okay, because your physical memory is very far away from your CPU, right? And whatever that is traveling cannot exceed the speed of light, right? And if you can travel at the speed of light, you can travel around the world 7 times in 1 second. So it doesn't mean that you can travel faster than that. Okay? You can only travel 7 times in a second. For your computer look at the speed of light, it is very slow. Okay? Let's say 1 gigahertz of memory, 1 gigahertz of processor, right? 1 gigahertz, one clock cycle, that means you can execute one instruction in 1 nanosecond. 1 nanosecond means 10 power of minus 9 seconds. Okay? In 1 second, if you travel on the copper electricity, 1 second, the signal can travel this long in 1 second. So for processor, the speed of light is very slow. Okay? And if we go to 10 gigahertz, it's even worse. Right? That's why in radio frequency, they keep on shrinking that's why our phone has an advantage, because we always use higher and higher frequency. As we go higher and higher frequency, the chip needs to be smaller and smaller because of this problem. Okay? Because when we transmit in terahertz, we not transmit in gigahertz, terahertz in the future. And of course, we have the technology already right now to do a millimeter wave, which is in terahertz. Okay, so that's the reason why L3 is inside the processor. Because when it's inside the processor, the distance between the CPU and the memory is only in micrometer. Okay, it's not in centimeter. Here, from here to here is about 3 centimeters. Okay, so I believe your processor is not 3 centimeters from your CPU, right? It's a bit further than that. So it needs time to travel. So that time is actually kind of slow. So if you are running at 1 gigahertz and you have to wait several clock cycles, basically you're not running at 1 gigahertz. You're running slower than that, right? So if you put your cache inside there, frequently used data inside. So whenever you need the data, it's inside the cache. So level 1 is the faster. Actually, level 1 run as fast as your processor. So if your processor run at 5 gigahertz, then your memory level 1 is also in 1 gigahertz. So if the data is already there, so you use it. This is only true if there's a cache hit. If cache miss, you still have to get from outside. All right? So that process is slow. But because you do you read the cache in page, right? One page. So most of the time, you have one cache miss, but you have multiple cache hit after that. So overall, you still have performance gain. Okay, so that is the use of the cache. Now there's a problem when we increase the number of processors. If we have a lot of CPU, and then you have a shared memory, then you have bus contention. And this is also a problem. That's why you don't see a processor that has bigger than 32 CPUs. Okay, so let's say this is your computer. Okay, and then you have multiple processors. I'm not talking about core. Inside there you got multiple core, but I'm talking about processor. So your computer, you can have multiple processors, right? And outside here you have your memory. Okay? And it is shared. Then your level 3, level 1, level 2 is all inside the processor. But outside here is shared by this different processor. Okay? And the bus that carry the data. Okay, you got address bus, you got data bus, you got control bus, right? So this bus has limit as well, in terms of speed and in terms of size. So if you have too many of them in there, whenever if all of them try to read the memory, even though they are different memory addresses, they have to wait for one another, right? So once they have to wait, that is bus contention. So if you have more than 32 CPUs, if one of them used, the rest of the 31 CPU have to wait. Right? So meaning that if you have more processor using the same bus, memory bus, then it will defeat the purpose. Even though your processor is running at 10 gigahertz, but your bus is slow. Okay? And each one have to go one by one, and eventually you won't gain any performance from there by increasing the CPU. So normally the CPU is very, very small. Let's say 16 CPU. What I mean is processor, 60 processor, 32 processor, and most. Okay? If you want to increase further, you can actually put you don't have processor, but you have multiple core. Okay? So up to date, we have the best for general purpose computer is Threadripper, maybe is 256 cores inside. Okay, and then the GPU, GPU has more. GPU has more than this, 2,000 cores. Okay, and there's a difference there. So for example, Threadripper, why they cannot increase? It's a bit harder for them to increase is because of the technology used to implement the CPU. It's more complex than the GPU core. The GPU core is much simpler than this core. Although they run at the same speed, or they may run at the same speed, but the implementation, the design is much simpler. Okay? It's not as complex as our Intel processor or AMD processor. Okay, that's why the size is normally smaller. But in the future, maybe it will be different because as we shrink the size of the transistor, we can pack more component inside that. That means we can increase further and further this size processor. But of course, you have to overcome this heat management issue. Okay, because in general too much heat, you cannot run as well because you have to manage the heat. Not only manage the power, you have to also manage the heat. Okay, so the shared memory performance, actually, when you share, you always have problems. Okay? If you don't share, then you cannot do distributed system, or you cannot do parallel computing. But when you share, you have problems. So what are the problems? The problem is the scalability. For example, I mentioned to you, if you've got mass contention, you cannot scale too much, right? And another thing is you need real time. For example, if certain things happen, you need to do it immediately. Okay? if let's say they need to communicate or the data is actually, or this computer is using this memory, the other one have to wait, right? So if you wait too long, you will exceed the real time needs, and then you will not do the job well. Okay, it can be something like this. Another thing is when you share the memory, especially if the memory is outside, then your performance can be great. For example, non-local. So level 3, level 2, level 1 is called local memory. This one is non-local. The external memory that is shared among all these processors, double DRAM especially, they are non-local. And non-local can be 10 times slower. Okay, so we have this. Actually, there's another one which is not here. Other issue is consistency. Okay, because when you share the data, let's say this value is 3, right? And then this processor use this value, so it will pitch into the cache 3. Okay, and then this processor is going to update this data 4. Okay, it depends on the algorithm. The algorithm that is used by this processor. This processor can do lazy write. Lazy write means it will delay the write because accessing the external memory is slow, right? So normally it will update only the copy inside the cache only. It will not update the external because it's slow. Because it knows that when you increase to 4, maybe you want to increase to 5. So it's pointless to write 4 and then write 5 again, right? So normally it will change very quickly here, but then it will change very slowly outside. So there's a danger of doing that because if let's say you don't update frequently, and this processor also read the stale value, which is 3. Okay, so this will have a consistency problem, which is not mentioned. Okay? So you have this problem as well when you do memory sharing. Of course, shared memory computing, shared memory allow us to do asymmetric multiprocessor parallel computing, right? Where we can actually develop software to break up the task into multiple tasks and assign to multiple processors to solve the problem. So that is the advantage. Of course, the disadvantage is those that I mentioned to you. And also another problem which we didn't talk about is the race condition. Okay, that is one of the major disadvantages. Not only what you see here, okay, the one that I mentioned here, consistency. Another one is race condition, which we will talk about in chapter 4 and chapter 5. Okay, so this is how the shared memory look like. Here, it shows only the thread. Okay, it shows only the thread that is running inside the process. So this is one process. One process. So the process also have multiple threads. Okay, so you have multiple threads. Thread 1, thread 2. So you can do multitasking within the process. You can also do multitasking across the process. Okay? Now across the process, the multitasking is normally slower because when you pass switch, you have to pass switch not only the process, you have to pass switch the virtual memory as well. Because the two virtual memory is different. It means you have to save it and then you have to load it. Of course, it is a lazy kind of saving and restoring. Okay? Whenever you touch, you start to push in and push out. But then the process operating system multitask is a bit slower than the thread. That's why here it says that threads are just like process, except that it's like why? Because thread actually live inside the process. Whatever this process sees, this thread is able to see as well. Okay? So this thread 2 is sharing the same address as this thread number 1. If let's say you've got another process, it has its own threads, and the thread is able to see its own memory. You cannot see other threads' memory in the other process. You can see the memory inside the process that is shared with other threads within itself. Okay, so you cannot see other threads, you can see only this one. Okay, inside there you will see something like this. So you got user space address. You also have kernel address space. Kernel is used by the operating system, but the user space normally is the one that all your thread is able to use. So whenever you call, let's say you create a thread, you can create two threads, thread 0, thread 1, and then you have thread control block, TCB. So you got the process control block, you also got thread control block. Now the thread control block normally is smaller, and you only store the register information. Okay? So whenever it pass switch between this thread 0 and thread 1, this register is loaded into the CPU and saved into the memory and load other threads context into the CPU. So whenever you do the task, you do that. Just like what I mentioned to you in the practical class. Okay? So that is how shared memory is used, because in threads, shared memory is much easier. Between processors is a bit more difficult because you have to use MMU to help you share the memory. Within the virtual memory, the MMU don't have to do any job because the thread is able to see the memory everybody is using within the threads. But across the process, the MMU has to participate in sharing the data or help the process see the data. Otherwise, it won't be able to see it. Okay? So here is a simple one, shared memory within the same virtual memory. Okay, this is an exercise actually. We have seen this. I'm going to skip that. I just tell you that these are the Pragma keyword that you can use when you parallel that all of you have learned. Some of you have seen for reduction. Some of you haven't yet. Maybe this week all of you will learn about for reduction. And schedule we're going to learn in practical 5. Scheduling. I will explain this later. And we also will learn about barrier. Maybe I'll teach you barrier much earlier so that you can use this barrier later on to help you solve a lot of problems. Okay, so this is basically just showing to you that how you run this program. Actually, this has nothing to do with what we are talking about there. This one is, I'm not sure why they do it there. Now I'll come back to distributed system. Okay, so just now is shared memory on single system, computer system. Now we want to talk about distributed shared memory. So distributed shared memory is shared memory, but not on the same system. Meaning that this is not the memory is not inside the computer. This memory that is shared is outside this computer, and maybe is in the network. Okay, so that is a distributed shared memory. And of course, if we have distributed shared memory, we have larger memory because you can share among multiple computers, and each computer, or maybe you can actually create one data center which is only consisting of memory or data storage. Right? Or maybe it can be something like this. This computer has a shared memory inside here. And then you have another computer who has its own shared memory, and then you can share this memory with this computer through the network. Okay? So that can be a distributed shared memory as well. But you need an operating system to help do this. That means this process that whenever you run out of memory, you can actually use the memory of another computer to store the data. And whenever you run the program, it looks like you're storing it with this memory. Actually, the operating system will help you, maybe through the help of memory and some other mechanism, to transport the data across to this computer and store it there. So whenever you want to touch or you use it, you can automatically read it and put it into your virtual memory. Okay, so for your process that see the computer, you thought that this content actually reside in the physical memory. Actually, it's not. So instead of going into the storage, secondary storage, okay, the distributed operating system can extend it. So not only in storage within this computer, this storage can be another memory in another computer. Okay, so the operating system needs to help do this with the help of MMU as well. So whenever your process touch this memory, you cause page fault, and then the operating system will catch it, and then you see that it's not there, and then you go and search, where is it? It's on another computer, so you will request from this operating system to give this data. So you take this data transport, put it into this memory, and then map it here, so that your process is able to use it. So for your process point of view, the memory is there. But actually, it's actually on another computer. Okay? So this is a shared memory, distributed shared memory. Of course, it's more complex than what is mentioned here. It's not mentioned here, that's why I mentioned to you, you can do it that way. Okay? But your operating system needs to be able to provide this kind of service. If it doesn't provide this service, then you don't have that kind of system. And that system is only available in distributed operating system. Okay? The one that I mentioned in lecture 1, which I missed. So the thing is, when you do distributed shared memory, you have to ask this question: how do you distribute the shared memory? For example, how do you store this data? And how many of them that read and write? And do you allow them to read and write? Because you need to authenticate, you need to have a assigned privilege. For example, if you're an administrator, you can use it, but if you're not, you cannot, right? So it's the same thing as this. So you can assign privilege to each one of the process, whether they can touch the memory or they cannot touch the memory. Okay, another issue that we need to look at is how do you replicate them and how do you migrate them when you need it. For example, let's say this computer use this data, this computer also use the same data, so it's shared, right? Okay? So in distributed shared memory, as I mentioned to you, whenever this process that is try to use it, try to touch the data, but it's not there, so you'll have to ask this operating system to give it, right? So this operating system will take this copy and send it. And this distributed operating system will put it into this new memory. Right now, you have replication, you have 2 copies. Okay, so that is replication. Okay, replication here is a must, because otherwise we're not able to share the memory, because they are in different locations. Right? So this is the replication that is talking about. You can multiple copies, and of course, you have issue with that again. Is consistency. For example, if I write, this guy will not be able to see that it's unique. Okay? So how does it solve it? Of course, you have to come to the operating system again. So for operating system, whenever you want to touch this memory, it knows that it's shared with somebody else and replicate. So you have to go and ask your operating system, is your data has been changed? If it is changed, please give me the latest one. So this operating system will check, yeah, it has been changed, then you pass it. So you pass it to this OS, and this OS will write into it before it allows the process to access it. So this must be done by the distributed operating system. You can see it's quite hard. When you replicate, you got issue, and the operating system has to handle it. Okay? Now another way, another issue, or maybe a feature of distributed shared data is maybe you need to do migration. Just now is replication. Now we want to talk about migration. Migration, it can be something like this. You've got a process that is running on this computer, right? Distributed operating system. And then suddenly this process feel that I'm not going to run here. I want to run on another computer. Okay? So you need to migrate this to this computer and then run on this system. Okay? Now if you're wondering why would you want to migrate at all? Okay? It's kind of silly. You run on one computer, of course run on that computer, don't migrate. You migrate why you want to find trouble, right? Okay, there is some use of that. Let's say for example, let's say I use Collab. Collab is cloud computing, and I run my process on Google Cloud. Google maybe has a cloud in Japan. Okay, let's say nearest to us maybe Japan. So I use Japan Google Cloud, and suddenly there's earthquake. Let's say for example, and the system realized that there is power outage going to happen very soon. what they can do is they can migrate my process immediately to maybe nearby, maybe to China, go to China. Without me knowing, it migrate to another process. So to me, I see the process is still running. It never stopped. Okay, but my process already migrated to another one. Okay, maybe here, after it migrated, I'll cut off. But for me, it's fine because I don't see any outage there. I see my process is still running. So migration can be important for this kind of situation. Another situation is, let's say for example, this process is running here, right? But then you always use the data here, and it's one continent away. Let's say this is Japan, this is America. So every time you have to transport a lot of data, gigabytes of data. So this process is always using this data. So why not move this process to here, nearer to the data? So that you can actually exchange the data, gigabyte or terabytes of data very quickly. So you might want to migrate your process. This is a second scenario. Okay? One is because you want to overcome issues like, for example, power outage or any kind of disruption. Second is you want to move closer to the resources. Okay? Because you don't want to transport the resources across the continent. Let's say America and Japan. You transport terabyte of data back and forth. Okay? So it's not efficient, right? So you move your process nearer to your resource so that you can actually use the data more efficiently, faster as well. So migration is one of the solutions, and we'll talk about this migration another time, another chapter. Okay, do I have time? Okay, so shared memory, of course, we have talked about virtual memory and all that. So issues like crashing, to avoid crashing. So this one, page in, page out crashing. This is also the same thing. This computer here used data which is in America. Also crashing, because why? You read the process, you write. You read the process, you write. This is also crashing. Okay, so crashing means this kind of situation. You have to overcome it. Okay, you have to travel different location. So you have to make sure that the process is actually nearby one another. Okay. And another thing is what kind of block size that you share. For example, in this case here, this page size here is very important because what the MMU do is kind of lazy. Okay, lazy right away. For example, if let's say I give you this memory, but you only have 1 gigabyte memory, right? So these are not filled. They are not filled. When you touch, then only you fill. So that is a lazy update. Okay? You don't touch it, you will not do anything. When you start to touch, it's not there now. Now you treat the data for the data. Okay? So if you have to do this, then your block size is important. This page size or the block size is important. If too big, then you have to read and write, page in and page out a lot. Because you just want to read 1 byte. Because the block size is 1 megabyte, but you want to touch only one byte. When you touch the 1 byte, you page in and page out. Sorry, page out first and then page in. So that you can touch that 1 byte. But you only touch 1 byte, and later when you touch another byte elsewhere. So it's going to be a lot of processing, right? But if you make your page size smaller, when you page in, page out, it's a bit smaller. Okay, so you have to determine what kind of size that you choose. The same thing here. When you move the data, what size that you choose in order to transport. Because too big the size, if you touch only 1 byte, you have to move 1 gigabyte of data, it's pointless, right? So you have to choose the proper size. Okay, why do you need to move 1 block? Because as I mentioned to you, is to make things are more efficient. For example, when you touch the first byte, most of the time you touch the second byte, third byte. That's why when you read and write, normally you write in 1 block or 1 page. Okay, you have to choose the location as well, because for example, in this case here, if this resources is in America and this one is in Japan, this is not a good location, right? 2 separate places where they have to share the data is not good. So you have to bring them together. So you have to do migration somehow in order to make sure that they are close by to one another and then use the data. Right? So right now you can see that migration is very important because when you have to reorganize your processes where it actually is located, you want to optimize it, you have to do migration. Okay? Of course, distributed memory programming, you can use message passing interface, which is MPI. We learned it in Practical 4, if I'm not mistaken. We can actually share the memory distributedly. Okay, one thing about MPI is you don't have to know. You can be just a process looking at the memory, and you do not know that the process is running on the same computer or different computer. Okay? Because MPI shield this computer. So when you run the program, you run it on a single computer or you run on different computer, it's the same program. Okay? So behind the scene, the API is doing the message passing work. And the data is shared between them and it gets transported, saved, or retrieved, and it's all done by API. You look at your data residing in your virtual network, but actually it's not there. The API helps you transport the data across the network if it is needed. Okay? So that's why this API is easy to use. Okay, so here I showed you, unfortunately in the practical we don't have exercise that use 4 different computers or 2 different computers. It's only one computer. But fortunately the program is the same. If you want to do multiple programs, you just need to issue a different command line interface. Okay? But unfortunately that one is not inside the program. Okay? But the program you don't have to change. If you have the same program, and if you do distributed or parallel computing inside the API, that same program you don't have to change. You just replicate it into multiple computers and then you run them. Okay? You issue the command and then all of them will work in a cluster, work together, and then they share the information, pass message among themselves without you knowing. Okay? In a program, it looks the same as long as it's running on the same computer. But of course, when you look at the code, you have to send and receive message. I'll show it to you. Okay, so here you have multiple programs, and they have data that is residing on different computers, and they can pass the data to and fro. Okay, and this is done by the computer. Sorry, the API. Okay, this one example. You got 2 MPI processors, and these 2 processors actually run maybe on different computer system. Okay? So this is data that is shared. This data is not shared. So you don't have to worry. The API, whenever it's shared, you just need to pass using message passing. That's all. Okay? That's the only thing that you need to do. Okay? If let's say you want to share the data, you have to pass the message. Otherwise, you just keep it inside your memory. Whether it is residing on local computer or other computer, you don't have to worry about it. The API will handle it. And here is the function that we're going to use. The first one is MPI send. The other one is MPI receive. Actually, here is asynchronous send, asynchronous receive. Actually, there is another one. Maybe the author did not write the other one. There are many functions. You got synchronous and asynchronous. So you got synchronous and you got asynchronous. Okay, you got MPI send. Okay. MPI is double S send. Okay, and then MPI I send. Okay, you got MPI receive. And then you have MPI equivalent of it is I receive. Okay, actually there are many more. There are another 4 here. I want to show it. I show only these these two. In the lecture, sorry, in the practical, we're going to use only these two. I don't think we have this. Now, what is the difference? This one, when you send, you wait until the receiver receives it before it returns, so that you can proceed. Okay? This one is different. When you send, you do not wait. You will return immediately. Whether you receive or not, your program will continue. Right? So that's why it's called asynchronous. So you can do any other job, and then you after that you can wait. You can wait for the receiver to respond. Okay? Here, whenever you call, you wait until the receiver receives, process it, and respond. Then only you can proceed. Okay? So synchronous and asynchronous that is the only difference. Here it shows to you the asynchronous one. But I think in a practical, we're going to use only the synchronous example. Okay, so this is a library. Actually, it's not standard library because it's not standard. If the standard is inside all compiler. This is not standard library. It's a library that is widely used. Okay, you can easily download it. It's free. Okay, but it's not standard library. And it's ridiculous because you can download free. Okay, Microsoft support it. Microsoft call it Microsoft MPI. Okay, we can download it. Linux has its own version, but they are compatible, meaning that you can run Linux, you can run Microsoft, and then you can run them in a cluster. Okay, you auto two different operating systems because the MPI is a library which is universal. Okay, that means when you write it, you have to conform to the protocol. So whether it's Linux, Apple computer, or Windows, they should be able to operate with one another. Okay? So this is one good thing about MPI is because it's heterogeneous. That means you don't need to run on the same operating system, even though it is. Okay? You can Mac OS, you can Windows, you can Linux, you can BSD, you can all sorts of operating system. As long as they support this MPI, they should be able to collaborate and solve the problem together. Okay? As long as your program is the same program in C++ that you write. So why do we bother to use MPI? Because it's so much easier. To do yourself using TCP, I think it's going to take ages for you to finish it, right? Because you have to handle a lot of things. For example, how do you manage the data transfer? How do you make sure that the receiver receives it? How do you respond? Okay, and how do you transport the data? What kind of protocol that you use? Okay, whether the protocol is reliable like TCP. If not, you use UDP. Are you going to handle it yourself? Let's say there's a packet that's missing. So all that we don't have to worry. Because MPI is going to help us do it. Our focus is to break our big problem, convert it into parallel computing, and then run the program. Okay? So we have less problem to worry about. This problem, the low level, we let MPI handle. Our focus is how to convert single thread program into multiple threads or parallel computing multiple threads code in order for it to solve the problem. Okay? So it's much easier to use. So you can see that all those that is listed here, we don't have to worry. Okay? For example, here we all use Ethernet, right? Maybe you all think, oh, Ethernet is the only communication media that is used, or maybe Wi-Fi and your telco too. Wi-Fi and also Ethernet. Actually, you go to different companies, they might be using different kind of communication media. They don't use Ethernet at all. Maybe they use InfiniBand. InfiniBand is not Internet. Sorry, not Ethernet. Then MyRenet also not Ethernet. Okay. Maybe they use ATM. ATM is not the auto communication. It's a different network communication medium called ATM. Right now, no more in use, but maybe bank is still using this communication medium. Okay, especially those old computers, they are still using ATM. Of course, ATM is no more in production. They get replaced by Ethernet. But MPI can work on all these different communication media. You don't have to worry about it, right? Otherwise, you have to worry what kind of communication media that you use. Okay, another thing is reliable. Whatever the message that you pass is, when it reach or it doesn't reach the receiver, the API will ensure that the data that is missing is get transported in until the receiver receives it. You don't have to worry about it. You just send it. Okay? Whatever that is happening in the network, whether the packet is broken, data is lost, connection is lost temporarily, the API will ensure that the data is transported and get received by the receiver correctly, reliably, and also in order. Okay, because your packet, whenever you send a large data, normally is broken down into multiple packets. As I mentioned to you last week, the network is not always always the same. It can change, so your packet can use different route to reach the destination. So when you receive, you might receive in different order, but API will make sure that when you receive, you will receive in order, even though that means when you assemble it back, you will assemble it in order. Although the arrival is not in order. Okay, another thing is what I mentioned before is completely heterogeneous. That means whatever operating system that you use, you're able to run that. Okay? So this is one example of the code. We haven't reached this part yet, but I already mentioned to you the message there actually. API send, which I mentioned there, and API receive. Okay. Okay. It's quite easy to use. You need to initialize it, and you have to finalize it. Okay. You have to initialize and finalize it before you start using any of the function. Okay. And then two important information. This is the one that we discussed in your practical 3, right? What is your ID? Your ID is here is called rank. In OMP it's called get num track, right? Here is rank, call it rank. And then the size is the num tracks. How many tracks is running at the same time in parallel. Okay, so these two information is given. It means whatever you learn in OMP will apply here as well. So you have to understand how OMP works in order to apply it. So here we use this ID, which is rank, and the size, which is the total size of your tracks. We use these two information to solve problems in parallel as well. Okay? So you can actually convert what we have learned in P3 into here. Okay? Just that the function call is different, but the techniques or the concept is still the same. Okay, except one part. Whenever you share the data, you have to send it, receive the data. Okay? In OMP, you basically don't do anything, right? Basically, you just maybe pass the data using function call. You pass maybe by using pointer reference, or you pass by value, right? Here you have to explicitly pass using mention passing. This is the only difference. The rest is the same except for this part. Whenever you send the data, you have to explicitly send as a message. Okay? So when we learn, we only focus on this part here because this is the only part that is different. So is this the only way to do distributed system? Because for MP cannot do distributed system. Actually no. There are many other platforms that you can use in order to do distributed system. This is only one of them. Okay? And this is maybe one of the most popular ones. Here is an example of code. I'm not going to it because we're going to cover this in practical. You can see that, just go through it softly. Here you initialize, and then you need to finalize. Okay, inside here, you can only call this function after you initialize. You cannot call this function before you initialize. Okay? The same thing, when you finish, you have to remember to finalize. If you don't finalize, you have error. Okay, this finalize is important. Why? Because in distributed system, let's say you've got two computers that is operating with one another. This one terminates, but this one does not realize that it terminates. Right? So that's why you have to call this finalize. So when you finalize, your MPI will communicate with other threads on the computer, telling the others that you already finished your job. Okay, you're done already. So that is the reason why we need to call this function to ensure that the rest of the threads that is running on another computer know that you already terminated. Otherwise, you'll be thinking it is either, right? Okay, so this will have a lot of problems, errors that can appear. Within 12 minutes left. Okay, so this I will discuss. Yeah, this is a way to run the program. Okay, you have to tell how many threads, or they call it processor, how many processors that you want to run here. You put 2, then you click 2. You put 10, you have to do it on the command line. It's unlike the OMP, you run it on the Visual Studio. This one you have to run explicitly run it on the line. Of course, you can run it in the Visual Studio also. That one maybe I'll show you later. Okay, if you want to run, you want to launch 4 processors, you just put 4 there. You can also run different number of processors. Okay. So this explains to you what's the difference between OMP and also MPI. They're basically the same. This one shared, this one not shared memory, this one is just passing. And MPI you can do distributed system, this one you cannot. You can do only parallel computing on a single computer. Right? Okay, but all of them require process identification or thread identification. Okay? Using this rank. Okay? And also determining what is the size of the processors or the size of the threads using the Okay, other methods to solve this is to use threads, p-thread. Have you all learned p-thread? We will learn threads later, not p-thread, maybe threads. Using thread, maybe we will learn also a little bit of p-threads. Okay, so there are other ways to do it. We can use p-thread to do concurrent processing. But p-thread does not guarantee parallel computing. It only guarantee concurrency. It doesn't guarantee parallelism. Okay? So this is one of the disadvantages of p-threads. But okay, your assignment, I know that your assignment allows you to use p-thread. Okay? That is because the previous lecturer put it like that. But now I tell you that you cannot use p-thread. Because if you use p-thread, in your assignment you have to show the performance gain. If you use p-thread, you won't see performance gain. Why? Because p-thread is concurrency. It's not parallel computing. And therefore you cannot get performance gains. Okay, so I ban you from using p-thread and threads. Okay, because later on you will tell me, I cannot get the result. Of course you cannot get the result because thread is concurrency. It's never parallel computing. Okay, so I know that is inside the assignment, but please make sure that you don't use p-thread. You can use OMP, you can use MPI, you can use GPU, you can use OpenCL. Okay, but threads and p-threads you have to avoid it because if you use it, you are guaranteed not to be able to get any performance at all, performance gain, because it runs on a single processor. It doesn't run on multiple processor or multiple processors. Okay? Okay, this shows to you the synchronous and sending and receiving. We will learn this later. And this is the message passing that's happening. And this one, unfortunately, we don't have it in our practical, is to send and receive in asynchronous mode. As I mentioned to you, sometimes when you send, you don't want to wait because you have other tasks to do, urgent tasks to do. So when you send, before the receiver receives, you go on to do your other task. Okay? And then after you finish your task, you might once a while go back and check to see whether the receiver already received and responded, and then you can action. Okay? So that is asynchronous sending and receiving. But we don't have example in most of the example is synchronous because asynchronous normally is a bit more tedious to program. But the way you program, maybe there's no example here. But you can check in the internet. Internet has a lot of examples about MPI, especially asynchronous. You can check it out. Okay? Although practical, you might want to use this in your assignment. Okay? So this is the difference that I mentioned to you. Send, receive, and then asynchronous. You got I send, I receive, and then you can wait. Okay, when you wait, what I mean wait, because when you send, it does not wait. Okay? So you can do other tasks, and then you can come back and check. You can come back and wait. Okay? There's another one that's missing, MPI test. MPI underscore test. Test is basically you don't want to wait. You want to test to see whether the receiver has already completed receiving it and respond. And if you test that the receiver hasn't responded yet, you can go on and do other tasks. If you wait, you start to call the wait, then you wait until the receiver responds. If the receiver doesn't respond, you wait forever. Okay, so asynchronous actually provide you two other, actually another one is MPI test. Okay, test and wait is more or less the same. Wait, you wait until once you call, you wait until the receiver responds. Okay, if you test, you can actually get away from it. That means if the receiver does not respond yet, you can do other tasks first and then come back and test. Okay, this one keep on coming back again and again, and this one you don't have to worry. Memory migration is done by AI. Okay, but memory migration, we're going to talk about this in practice. So in chapter 4, we're going to talk about how do we do memory migration. I think this is the last slide. When we migrate, we can stop and copy. That means we stop this program, we copy across. Once we copy the data across the program to another computer, and then we restart the program. Continue from where we start or restart all over again. So during that period of time, when you transfer, the system will not respond. Okay, that is stop and copy. Another way is concurrent copy, meaning that while you are migrating, you are still running. That means if let's say you are serving somebody, let's say it's a web server, you still respond to the customer, to the client, while it is migrating. So once you migrate everything already, you will stop and then immediately switch to here and then serve the customer. So to the customer, concurrent copy is more has better user experience because you don't see the process stop. Okay? Okay, copy or reference is slightly different. It's kind of lazy copy. So when you migrate, it will migrate only the one that is touched. Let's say, for example, you migrate already, right? So the client actually was here before. Right now, when you migrate a little bit only. You migrate only the program that is serving the customer. So the customer will be served immediately. But your old data and some of your program is still in your old computer. But you're running here already. So whenever you touch some memory that is not inside here, you will copy. So you copy on reference. So when you touch, you copy. Okay, so you copy, eventually you'll be in full program. But there is another still copy that is at the original computer. So there are two ways to make your user experience better. One is concurrent copy, the other one is copy on reference. Concurrent copy means you keep on copying until finish and then you stop. Copy on reference is different. You only copy the one that is running, but your old copy is still there. How long you leave it, you don't care. And you don't really mind as well. And then it's served. Whenever it touches the memory, you just copy over. But eventually, when you copy everything, it will stop. Right? But then, this copy can stay there for a very, very long time. Right? Because you copy on reference. When you reference, then you copy. Okay? So this is, I think, the last slide. I think to give you 6